Okay, we are off here to chapter 14, which is also known as the never-ending chapter. So it goes on and on. And just when you think it's almost done, it still goes on and on and on. So I would say probably in most books, chapter 14 is like two chapters, kind of broken apart. So we're going to kind of do it in parts as well. So if you seem like we're on chapter 14 forever, it is not your imagination. It is going to be a long chapter. So we're going to talk about acids and bases in this chapter. We're going to talk about pH, pOH, all that kind of basic acid and bases. We will get into weak acids and weak base calculations. We'll also talk about salts and hydrolysis, and then we'll get into buffers, and then we'll get into titrations. Oh my, a bunch of stuff going on in this chapter. So we're going to start here with the beginning part here, which is just some basic sort of acid and base chemistry. So let's talk a little bit about acids and bases in general. Acids have a sour taste, things like vinegar, which acetic acid is the major sort of component. Citrus acid there in fruits. They react with metals to produce hydrogen gases in reactions that you probably are familiar with, like take a little bit of zinc and some hydrochloric acid, right? Zinc will come in and kick out the hydrogen. We'll produce some hydrogen gas, which is the bubbles you see when you've done this hopefully before. Make a little zinc chloride, a little balancing like I'm in chemistry class. There we go, with something like that. So that's a very common sort of reaction. Again, in order for example, this reaction to take place, the zinc has to be more reactive than hydrogen. Otherwise, it will not take place. For example, if you did this with copper, it would not take place because copper is less reactive than hydrochloric acid. They used to years ago do an experiment in Chem 50. I don't think they do it anymore with pennies. They would used to give you pennies, an old penny and a new penny, and they would file it. You would file the pennies. Then you would dump it into a beaker of hydrochloric acid. They don't do that anymore, right? I don't think. So old pennies are made up of what? Old pennies are made of copper, right? New pennies are copper on the outside, zinc on the inside. Yeah, so it's kind of cool experiment. You file it, put it in there, and your new penny would kind of disappear a little bit there as it would basically react with what's inside and stuff like that. They also react with carbonates or bicarbonates to produce carbon dioxide. So, for example, we take a little hydrochloric acid, maybe a little sodium carbonate, a little double displacement type reaction happening, right? Positive, negative, guy, positive, negative. They're going to switch partners. Make a little sodium chloride and a little carbonic acid. And it's the carbonic acid here, which really will not hang around a very long time and will go through a decomposition reaction to produce CO2 and water here. And again, plop, plop, fizz, fizz, little Alka-Seltzer type action, that type of thing. Now, speaking of acids, we should also just review really quickly here about nomenclature of acids, right? And naming acids just to make sure so you don't say like this thing, right? Hopefully. As you might remember, right, acids again all revolve over whether or not there is oxygen in the acid. And if the answer is no, there is no oxygen, then the acid should be hydro something ic acid, like HCl would be hydrochloric acid. HBr would be hydrobromic acid. Remember that for all acids, the cation is H plus, right? And the anion in this particular example would be the negative guy there, which would be our bromide ion in this particular case. We also typically put aqueous next to an acid to indicate that it's in solution, because if I had HCl that say was in the gas state, we would call that hydrogen chloride, right? So that'd be hydrogen chloride gas. So So we should, and you should get in a habit of putting the aqueous symbol next to any type of acid to indicate that it is an acid and that you're dealing with. Also, if it does contain oxygen, it most likely will contain a polyatomic ion. And again, your polyatomic ions basically end in one of two ways. Either it ends in 8. And if your polyatomic ion there ends in 8, your acid would be something ic acid. So a little HNO3. NO3 is nitrate, which means this would be nitric acid. H2SO4. SO4 is sulfate, which means this will be sulfuric acid, right? Now, if your polyatomic ion ended in ite, your acid would be something OUS acid, right? And if you had something like HNO2, that is nitrite, which means this would be nitrous acid. Questions on naming? Yeah. Yeah, you ate too much, you feel icky. It's a good way. That's how I teach it. Actually. Yeah. So, other questions or anything now? All right, so you should obviously be able to properly name acids and recognize what they are rather than acid or that thing over there. All right. There's our 3-minute naming of acids. Bases, on the other hand, they feel slippery. A lot of soaps are bases. Things like drain cleaners are bases. You could go like Home Depot and buy just straight sodium hydroxide to clean your drain, believe it or not. There's a lot of warnings on it, but you can use that to do that. A lot of bases do come from group 1 and group 2 on the periodic table. Group 1 is the alkali metals. Group 2 are the alkaline earth metals. The word alkaline pretty much means basic. So a lot of our strong bases, for example, come from group 1 and group 2 on the periodic table with hydroxide in them. By the way, they also turn litmus paper different colors. Litmus paper is paper that we use to figure out whether or not a solution, for example, is acidic or basic. It will not tell you the pH or anything like that, but it will tell you if it is acidic or basic. Pretty much if you put anything on your litmus paper and it turns red, that means it is acidic. And if you put it on your litmus paper and it turns blue, that means that it is basic. So a lot of times if we're measuring something that we think is basic, we'll use red litmus paper to turn it blue. And if we're measuring something that we think is basic, we'll take blue litmus paper and try to turn it red. There's also neutral litmus paper. It'll go either way. It's kind of like a purplish color in a lot of cases. Any questions on that? I think we use litmus paper. Not yet. We will. But I don't think we have done it yet, but we will. All right. So let's talk about the definitions of some acids and bases a little bit more. Sort of the early definition of acids and bases was an Arrhenius definition. He did a lot of work with electrolytes, as you may remember. Electrolytes are things that when they go for a swim, pretty much will break apart into ions. They'll conduct electricity because of the presence of those ions in solution. So he said that basically a acid is something that has the ability to produce H plus or H3O plus ions in solution. So when we talk about something being an acid, we're really talking about the ability of it to produce basically free floating H plus molecules, not attached to anything, just kind of floating freely in the solution. And that's something that is a pretty good acid. Now, when we talk about acid-base chemistry, there's a few things. H plus and H3O plus, which is the hydronium ion. And this is obviously our hydrogen ion. They're pretty much the same thing. and they're used interchangeable in both equations and also formulas. I will tell you personally, for me, I use H plus most of the time. But anywhere I kind of put H plus, you can put H3O plus. A lot of books nowadays use H3O plus a lot rather than just H plus, but they are sort of interchangeable. The real difference as to whether or not, for example, you kind of will get H plus versus H3O plus is really sort of how you write your equation and whether or not you sort of include water in there. So for example, this is hydrochloric acid, which is a strong acid. And hydrochloric acid, when it is in water, will basically break apart. And the result of that is, in this particular case, it will actually send a H plus over to the water. And that will produce your H3O plus and your Cl minus. And really, this is nothing more than just an equation that's showing this strong acid breaking apart in solution in water. Now, you could write this exact same sort of strong acid breaking apart by just writing HCl goes to H plus and Cl minus. So these are really equivalent sort of equations for basically just this acid breaking apart in solution. Obviously, here in the second one, I did not put the water in. So I did not get H3O plus, so I just got the H plus. So again, they basically are equivalent to each other, and you can write it either way that you like. As I mentioned before, I personally will probably roll with this sort of writing here with just the H plus. But again, if you want to put the water in there, you can. So a acid is any substance that has the ability to produce H plus or H3O plus. By the way, H plus is also referred to in acid-base chemistry as a proton, and that is because hydrogen has how many protons and electrons? And in this case, it has how many neutrons, hydrogen? It has none, right? So hydrogen has none. And as you correctly said there, in this case, as it is positive, it had to lose its electron to do so, which leaves it just a proton in this case, right? So that's why it's also referred to as a proton. The Arrhenius base is a substance that has the ability to produce hydroxide in solution. And again, much like the acid, what we're talking about is the ability basically to get some free hydroxide basically floating around in the actual solution here. In this case, what's going to happen is the ammonia plus some water. Ammonia is actually a weak base, and the ammonia is actually going to accept an H plus from the water, and that is going to produce our hydroxide. And over here in the top one where we have our acid, we have our H plus or H3O plus. As we go through this chapter, sometimes people are not sure what values, for example, to use in calculations. Should they use more of the acidic sort of value or the basic sort of values? And seeing these equations can really help you decide which one you should be doing. And that is when you look on the left-hand side of the equation and the product side, if you see H plus there or H3O plus, that's really an acidic type situation, and you should really be doing calculations involving an acid. If you look on the right-hand side of the arrow and you see hydroxide, that is definitely a basic situation, and you definitely should be doing some type of basic calculation. So these equations are important to know how to write them correctly, and they also give you some important information. Now, Arrhenius's definition here was a good one, but he did a lot of work with really strong bases and things that contain hydroxide. And as we saw there with ammonia, for example, you don't actually need to have hydroxide in the actual formula. So this brings us to really a more sort of general definition of an acid and base, and this is the Bronsted-Lowry definition. The Bronsted-Lowry definition of an acid is a proton donor. So that is something that will give away not just an H, but the H plus is important part of that because it will change the charges on everybody as that positive charge kind of moves around as well. A Bronsted-Lowry base is something that will accept a proton. So in this particular case, as I mentioned before, the water is actually going to send the H plus over. And that is going to make our NH3 the base in this case. The water here will actually act as the acid. And sort of the consequence of the Bronsted-Lowry definition of an acid and base is it will actually make partners on the other side, which are known as the conjugate acid and the conjugate base. So the base on the left-hand side, its partner on the right-hand side is the conjugate acid. And the acid on the left-hand side, its partner on the right-hand side is the conjugate base. So the relationship between those two things is that. And what I'll do maybe is get rid of those writings. So again, this is our conjugate acid and our conjugate base. And again, these are the relationships here. So what is the difference between a acid and its conjugate base or a base and its conjugate acid? The difference is pretty much this guy right here, and that has to be the only difference is 1H plus. So in order for something to be pairs or related to each other in the Bronsted-Lowry definition, the absolutely only difference there could be is 1H plus difference. So if there's more than 1H plus difference, they are not related to each other. They're not considered pairs. When we look from the base to the conjugate acid, it has one more H plus than it started with. And when we go from the acid to the conjugate base, it has one less H plus than it started with, as it obviously sent it over there to our base. Any questions on that there? All right, so why don't we try some here? Out of this list, take a moment here, choose any ones that are conjugate acid base pairs. Let's see what you come up with here. Okay, so let's take a look. Let's take a look at the first one here. We got us HCl, and we got us, I don't know why books always write it this way, but ClO minus basically. The difference here is definitely an H plus difference, but there's also a difference of an oxygen. And that clearly means that these guys are not related to each other. So again, because one has oxygen, one doesn't, they're definitely not related to each other. How about H2SO4 and SO4 2 minus? Are they pairs? They are not pairs. The difference here is 2 H pluses, right? And that would not make them pairs, even though they are related to each other. But that is too far to make them sort of that acid conjugate base pair. Now, something like that, which is sulfuric acid, is a diprotic acid, which means it can lose 2 hydrogens. And by the way, the hydrogens actually come off one at a time. They don't come off both at once. So what happens first is this guy will drop off one of its hydrogens and make something like this. And then this guy here will drop off its second hydrogen there and make something like this, a little sulfate and H plus. Is it easier to get rid of the first hydrogen or second one? Which one's easier? First one is much easier because after you get rid of the first one, you now have something with a negative charge, right? And trying to rip off something that's positive, not going to happen so easily. That is why when we look at something like H2SO4, this guy and this guy, right, are related to each other and they would be pairs. This guy here and this guy here would also be pairs, but going directly here is too many steps in a row, so they are not going to be related in that case. Any questions on that? Yeah. Hydrogen sulfate. Yeah. Or bisulfate, kind of like HCO3. We have next one there, which is our NH4 plus NH3. Are these guys related to each other? They are. The difference here is 1H plus. You can either take the H plus off the guy on the left, and that leaves you NH3, or put the H plus on the NH3, and that gives you NH4 plus. So that's a winner there. And H3O plus and OH minus, are they? No, that's a couple hydrogens down the road as well, so not so good. And clearly we had 3 worked, so that's not right. So looks like only 3 here is a pair. Any questions on that there? All right, let's take a look at this one. Aniline C6H5NH2. What would be the form of its conjugate? It's, clearly you should know, H plus is pretty much what you need to do here. Either you got to put it on or take it off. And that sometimes is a hard thing for people to know. And if you remember sort of our relationship that we just saw, our acid plus our base makes our conjugate acid and conjugate base, where these two are related to each other and these two are related to each other. By the way, regular acid and bases on the left-hand side of the arrow are your conjugate partners. On the right-hand side of the arrow usually is where you find them. So if they weren't nice enough to tell us what this is, we know that we want the conjugate acid. So that means if I go backwards, what I am looking at in this case is actually a base. And I can use the Bronsted Lowry definition of a base, which means it should donate, right? Or sorry, it should accept a H plus as it is a base. So we actually want to put the hydrogen on in this case, since this is a base. So we'll add 1 hydrogen to the end, and it will also again have the plus, which looks like maybe number 2 would be the right choice here. So again, because this is technically a base, we want to add the H plus. And obviously you can kind of think about it backwards. They won't always tell you what it is. They'll just ask you, to give the conjugate acid or conjugate base. And again, if you're not sure, you can kind of think about it backwards. So for example, if we did have our like HCO3 minus, for example, let's say we wanted the conjugate acid for this guy. And then we also want the conjugate base for this guy. So take a moment and write the formulas for each of those, starting with a little bicarbonate there. Okay, so let's take a look at it. Once again, if you're not sure, we could take a look. We'll do the conjugate base first. So if I'm looking to write the conjugate base, if I think about it backwards, in this case, this is going to act as an acid, which in this case would donate an H plus. So it's going to give away an H plus. And we are going to end up with CO3 2 minus, which is carbonate as its partner. Now, just like we did on this problem, if I'm looking for the conjugate acid going backwards, that means that this is going to act as a base in this case, which means it's actually going to accept an H plus. And that means I'll get myself there a little carbonic acid. Any questions on either of those? So this obviously is something that can act as an acid or a base, and that is what is known as being amphoteric. An amphoteric substance is a substance that can act as an acid or a base. We actually saw it earlier with our friend. Whoops, get back here. There it is. We saw it earlier with water here when it was written with the hydrochloric acid. In this case, it was going to accept an H plus, which again gave us our H3O plus and our Cl minus. We saw it with water when it reacted with ammonia. In this case, though, it is the water giving away the H plus, and that made NH4 plus and a little hydroxide. So water as well can act as an acid or base, as an amphoteric substances. A lot of other things besides water, a lot of things like this that have a hydrogen and a negative charge, oftentimes can act as an acid or a base. And that's because they have a hydrogen to give and they have that minus charge, so they can kind of accept the hydrogen in with it. So like HSO4, that minus that we just saw, also can kind of go both ways. And we'll talk about later on in this chapter how you decide which way it might go in a situation like that if you come across it. Any questions on conjugate acid base pairs? So speaking of water, water obviously, as we just talked about, can act as an acid or a base, which means Water can even react with itself, one being the acid and one being the base. So in this case, this guy's going to grab off hydrogen. He's going to get rid of a hydrogen. And again, it's going to make H3O plus and hydroxide. This is what is happening with water in just solution to begin with. It's referred to as the autoionization of water. Dare I see a reversible reaction happening there, which means it could come to equilibrium, which means we can have an equilibrium constant for the reaction of water with itself, which is known as Kw. And Kw is the equilibrium constant for water, and it is a useful sort of relationship that we use to help us decide in some cases what the solution is. Is it acidic, basic, or neutral? So when we write this like normal, we do not include our water, which is a pure liquid, which means our Kw would be the concentration of H plus times the concentration of OH minus. And for the most part, it equals 1 times 10 to the minus 14. And I will say that, for most cases, you can kind of think of it as a constant. You always have that available to you, the 1 times 10 to the minus 14. But as we talked about with equilibrium constants, if the temperature changes, so would the value of Kw. So I would say probably at 99% of the time, 1 times 10 to the minus 14 is going to be the number that you're going to use for Kw. But if it happens technically not to be 25 degrees Celsius, or if they tell you a different temperature, you could have a different value for Kw, and they probably would give it to you or reference you to a table to look it up or something like that. But again, probably even more than 99% of the time, 1 times 10 to the minus 14 is going to be the one that you're going to use it. So we can actually use this Kw expression. And once again, this formula here could also be written as H3O plus times OH minus times 10 to the minus 14. Really, the H plus or the H3O plus is the acid part of the solution. OH minus is the base part of the solution. The relationship between H plus and OH minus is an opposite relationship. So as one goes up, the other goes down. So they go opposites of each other. So the more H plus that you have floating around that solution freely, the less OH minus you have, and vice versa. The more OH minus you got in that solution, the less H plus you will have. So we can actually compare the concentrations of H plus to OH minus in a solution to help us decide if the solution is acidic, basic, or neutral. If you happen to calculate the H plus concentration and it equals the OH minus concentration, which at 25 degrees means they both will equal 1 times 10 to the minus 7 molar. It will be a neutral solution. If you calculate the H plus concentration and it's larger than the OH minus concentration, so the acid part is larger than the base part, that means that the solution will be acidic. And if you compare the concentration and your hydroxide concentration is larger than your H plus concentration, then it will be basic. We could use this as a formula where the H plus concentration would equal Kw divided by the OH minus concentration. Or if you wanted the OH minus concentration, it would be Kw divided by the H plus concentration. Once again, Kw would be the 1 times 10 to the minus 14. You definitely want to make sure exponent button being used in this chapter for sure. Otherwise, it's going to be an even longer chapter for you than it is normally. So make sure you definitely punch all this stuff in with your exponent button. So let's try it. What is the concentration of hydroxide here? If the hydrogen ion concentration is 1. Okay, let's take a look. So here we have the hydrogen ion concentration is 1.3. We probably want to calculate our hydroxide concentration here. So again, that Kw is what's going to allow us to do that. And in this case, we have the H plus, so the hydroxide concentration would equal basically our Kw divided by our H plus concentration, which would give us, again, making sure you use your exponent button there. One exponent button, negative 14 divided by 1.3. Going to give us a 7.7 times 10 to the minus 15. We do need units as it is a concentration, right? In this case, the solution would be acidic, basic, or neutral. Definitely would be acidic, as in this case, right? The H plus concentration is much greater than the OH minus concentration. So it's going to be acidic, which I would hope, since it is hydrochloric acid. Yes, in that case. Any questions on that? All right, let's try one more here to finish it up. We have an H plus concentration of 1.2 times 10 to the minus 6. What is the OH minus, and is it acidic, basic, or neutral? I'm assuming the right answer is up there somewhere. Yes. Same deal here. We're given the H plus, and we're looking for our OH minus concentration here. So once again, our OH minus will equal our Kw, which is 1 times 10 to the minus 14, divided by our H plus, which is 1 times 10 to the minus 6. The good news is the same calculation regardless of which one you're given. And if you do all that good stuff, you should end up with 8.3 times 10 to the minus 9 molar as your concentration. Or if your calculator ran out of room, you have like 1, 2, 3, 4, 5, 6, 7, 8, 0, something like that on your calculator. So again, if you're in scientific notation, that's how you'll get to the 8.3. If not, a lot of calculators will run out of space and just have like the 8 at the end there. So that leaves us these two. So in this case, we want to compare the H plus concentration to the OH minus concentration. Which one's larger? The H plus concentration is larger in this case. So a reminder, right, that when you're comparing numbers that have negative exponents, the negative is important. So as I just mentioned, this guy is 9 places this way. This guy is only 6 places that way with zeros, right? So it is actually a larger number. So with negative exponents, the smaller negative exponent is actually, again, the larger number here, which means that this should be acidic, right? Here in this case. Any questions on that there? All right, we'll lay it up there for today.